Hi there. Continuing in our geometry journey, we are going to look at tessellations today, a little bit about them. And after you've viewed this video and done your homework, you have a project too to do, which I think is fun, and I love seeing the results that students get. They're very pretty usually. And if you're an art student, you might have done a project like this in one of your art classes, but like I think Professor Holly Scoggins does one. But anyways, pretty cool. Look forward to seeing that on Canvas. But in the meantime, let's tell you a little bit of background information about tessellations. A tessellation is also called a tiling. And if you're like me, you immediately get a little picture in your head. Now here, tiling, I picture first a bunch of square tiles on a floor. Then I start to picture, like in downtown Tampa, Ybor City area, I might picture like the Spanish tiles that might be in some of the restaurants or other buildings there. And then my mind kind of wanders and then starts to picture something. One of my former stepmother-in-law was an artist, and she had this nice mural kind of patio that she made with broken tile. So that's the kind of things that pop in my head, these images like rapid fire. But in mathematics, I mean, you're not far off when you picture those images. Those are examples of tilings in mathematics too. Because tilings are patterns formed when you have these geometric figures that are used to cover an entire plane with no gaps. So you're taking a flat surface and you're using geometric shapes to fit together, kind of like a puzzle. You know, they fit together. There's no gaps, no overlaps. The tile floor, I guess technically you have gaps with the grout in between the tiles, but it's still those shapes that with the grout fills it in and gives you still a nice, I mean, you don't want your tiles overlapping. They fit together nicely and fill up your whole floor space. Your floor is like a finite version of a plane. A plane's flat like that, but it's infinite and keeps going in all directions. Also, technically, a plane has no thickness, so your floor is not a plane, but it's a nice way to think about one. Some other examples in real life you might see are solar panels, which there's, I believe off I-4, there's a solar farm that went up a few years ago. I'm driving along, I think that's where I saw that. Or, you know, if you see honeycomb, I think everybody's familiar with honeycombs. And there's all kinds of examples. And if you're familiar with M.C. Escher, many of his pieces of art involve tessellations or tilings. Or they involve him taking tessellations and doing some interesting things with them. Alright, so I mentioned a tile floor and I mentioned a honeycomb. There are actually only 3 regular polygons that tessellate. And when I talk about square tiles, that's an example of one of those regular polygons. In a regular polygon, the sides and the angles are the same. So a square has all 4 sides the same, all 4 angles the same. But there's only 3 of them that tessellate. So I'll go ahead and draw your square, the one I just mentioned. Beware, I am not an art major. Not actually taken any drawing classes ever. So my drawings are not to scale and they're not perfect. But your square, you have 4 angles that are right angles. You have 4 sides that are the same length. Mentioned honeycomb. Honeycomb is an example of a regular hexagon tiling. So 6-sided figure. Cool story. Bees do not actually make hexagons in their honeycombs. I know you're probably told that your whole life. Turns out they actually make cylinders. That makes a little more sense when you think about it. They're able to make these tubes around their bodies. And then those tubes, to optimally fill the space, they settle into that pattern along like that. You have the row of tubes, and then the next row kind of settles in on top of those, but staggered a little bit. And then the next row settles in on top of those, kind of staggered a little bit. Kind of like if you try to stack up like a bunch of bottles, if you can get kind of a pyramid shape, but you know how they like settle into the crevices between bottles. That's what's basically happening with these. And then the soft honeycomb kind of spreads out and fills in the available space. And it ends up taking up the shape of a hexagon. Each one takes up the shape of a hexagon because that hexagon ends up being the optimal fill in of that space. That's just like a natural progression from the cylinder. So your regular hexagon, all 6 angles are the same, all 6 sides are the same measure. And then also an equilateral triangle. All 3 sides are the same. And if it's equilateral, then all 3 angles are the same. It's also equiangular. Those are the only 3 regular polygons that tessellate. Okay. All right, some examples of how they would tessellate. I mean, like I already mentioned the tile floor. Often on a tile floor, you walk in and you see these squares just all lined up on the floor like this. Or with your honeycomb, you have your hexagons that settle in. Kind of like this. And so forth. Your equilateral triangles, you start to do enough of those, and if you follow a certain shape, you can basically end up with a hexagon. Like you can do them like this. There you got a hexagon. Kind of reminds me of the Trivial Pursuit with the little wheel, the little pie or whatever. Let me do a few more though on there so it doesn't look so much like a hexagon. And keep in mind, these are supposed to be equilateral. I am not a good artist. But there's some examples of the way you might see these regular polygons tiled. And in fact, the examples I just did are all edge-to-edge tilings. They have a name. Because the way I laid them out, entire edges are up against, perfectly matched up against entire other edges. Like this top left square, or top left square, the bottom edge is perfectly aligned with the top edge of this bottom left square over here. Or in the hexagons, one of the hexagon sides, edges, is perfectly aligned with another hexagon sides or edges. And that's true for all of the polygons we're using in these particular tilings. So these are all edge to edge. But you can draw the squares and the triangles to not be edge to edge. Because you can take the squares and you can draw them kind of offset, and that would still be a tiling. Because still, as you draw, you can keep going and you fill in a plane. This kind of reminds me of a brick wall, how the bricks usually are. Again, these are supposed to be squares. Sorry, they don't look like it. But these down here are not edge to edge. And the triangles too, you can do those so they're not edge to edge if you want. So at first it looks like it's going to be when I'm doing this little row here. But then on the bottom, I can always just repeat that same row. See how that looks? So with the ones that are not edge to edge, what happens, let me take some color here, is you'll have like half or part of an edge matches up with part of an edge of another. And then the other part of an edge of one matches up with a different part of an edge of a different one. So it's not fully flush. The edges aren't fully flush against each other. You can see that in the triangles too. Like right here you have half an edge lined up with half an edge. And then right here you have another half an edge lined up with a different triangle, half an edge of a different triangle. Those are not edge to edge. But the ultimate question you probably have in your head already is, aren't there more regular polygons out there? And why is it only these 3? Why is it only these 3 for regular polygons? Now I'm just talking about regular polygons right now, because you can have all kinds of other tessellations. Just with the polygons out, all the edges are the same length and all the angles are the same measure. Why is it only these 3 for regular polygons to tessellate? Well, that has to do with their angles. If you took MGF 1106 already, you learned about this. If you're taking it now, you might have not learned about it yet, but you will. Or if you took it a while back, you might be like, I don't remember, but that's okay. Let me tell you why this works the way it does. All right. We have some different regular polygons. Like triangle has 3 sides, 3 angles. Your square has 4 sides, 4 angles. Your pentagon, regular pentagon, has 5 sides, 5 angles. Well, all pentagons have 5 sides and 5 angles, but regular pentagon, all the angles are the same and all the sides are the same measure. Regular hexagon has 6 sides, 6 angles, and so forth. You have a heptagon that has 7, an octagon that has 8, nonagon has 9, decagon has 10. You can go high. You can go as high as you want. In fact, ancient mathematicians would do these thought processes where they would imagine what would happen if you could go out to infinity with a number of sides with polygons, and they were able to develop all kinds of geometric concepts as well as calculus concepts by thinking that way. Dodecagon, all kinds of cool stuff. Icosagon. All right, so we'll just stop there for the interest of time and space, because I can demonstrate my point with just these. If you take the angles inside of each of these regular polygons, you learned early on that a triangle's angles inside, those 3 interior angles, add up to 180 degrees. All right, my little U didn't turn out so great there. Let me erase that and rewrite it for posterity. Okay. So those add up to 180 degrees. Now, if you look at your square, you're like, well, I know each of those is 90, so 90, 90, 90, 90 has to come out to a total of 360. And you can also make some deductions about each angle, since we're talking regular polygons and the angles are all the same. Well, if the total is 180 in a triangle, divide by 3, each one's 60 in the equilateral triangle. If the total is 360, we know squares are each 90. But then what's going on with like a pentagon or a hexagon, as we go higher? Well, if we use the same vertex and draw segments to the other vertices, we can divide each of these image shapes into smaller triangles. This is a trick used a lot in geometry where, you're thinking about the original shape might be complicated, but if we can break it up into smaller, more familiar shapes, sometimes we can get somewhere with it. And that's exactly what happens here. Your square can be broken up into 2 triangles. So when you do the sum of the interior angles, you've got 2 triangles whose interior angles are each 180. So 2 triangles gives you 180 times 2, which is 360. So we can use that principle with the pentagon. We can start with one of the vertices and go from there each time and draw some triangles by connecting to other vertices. And by doing it that way, we make sure that the interior angles in each triangle will represent the interior angles in that pentagon too. So we've got 3 triangles there. The interior angles of each is 180, and those interior angles in those triangles make up the interior angles in the pentagon. So we can multiply there and get that the pentagon has 540 degrees total. Which, if all 5 angles are the same, 540 divided by 5 is 108. So 108 degrees each. Hexagons, start with the vertex, start drawing segments out to other vertices. This way you can draw your triangles that their angles make up the angles of the hexagon. You end up with 4 triangles times 180 degrees inside of each. Gives you 720 degrees in the hexagon. 720 divided by 6 tells you that each angle is 120 degrees. And you could do this for all regular polygons on up. In can be the number of sides and angles. And notice that the number of triangles is n minus 2. Multiply that by 180 to get the total of your angles. And then you can take that total, whatever that was, and divide by your number of sides, the number of angles, n. And that'll tell you what each angle's measure is. So what does this have to do with anything? Well, if you start to look at your tessellations, earlier I drew the one with triangles. Let's draw that again. Let's sketch a triangle one again. I'm going to go ahead and just sketch an edge-to-edge one again because that'll demonstrate this the best. Oops. If you look at where the triangles meet, like in a vertex, you'll notice that, like in this where I just drew the little blue dot, you've got 1, 2, 3, 4, 5, 6 angles there from 6 different triangles that have to come together into that vertex. And since there's no gaps and no overlaps in this tessellation, those angles have to be able together to make a full circle, or 360 degrees. So that's the key. You have to be able to bring your vertices together on these tessellations so that the angles that make up that space around that vertex will add up to 360, because you need to be able to go all the way around smoothly and evenly. So in our triangle, each angle was 60 degrees, right? And there's 6 angles. 60 degrees times 6 is 360 degrees. And when we did our squares, it's the same idea. Once again, I'll just do edge to edge because that's the easiest way to demonstrate this, why it has to work this way. Oh, a lighter blue. There we go. We have these 4 angles here, each 90 degrees. Times 4 is 360. If you do your hexagons, your honeycomb, we know that each hexagon angle is 120 from up there. So 1, 2, 3 angles of 120 each. So that's 360. And so on. So those 3 are able to do that. Now, if you try to take any others, we'll take the pentagon and try to do this. If you try to take any other regular polygons and you try to tessellate them, you run into some trouble. A pentagon is a classic example of this. You try to draw your pentagons, start trying to draw them together. Again, I'm not an artist, so this is really hard for me. You don't see it, but I'm actually turning my iPad around. Thankfully, it's letting me do that. But you're going to find that if you try to do 3 of them, you end up with a gap. If you try to do 4 of them, you end up with an overlap. Because what did we say the interior angle was? One of them's 108. So if you have 3 of the interior angles here of 108 each, that's only 324 degrees. That's under. And if you try to do times 4, you're going to get 432 degrees. That's over. So as soon as you try to do 4, you're going to have an overlap. You can't do that. You don't want a tile floor where tiles are sitting on top of tiles. It's ugly and dangerous. And then eventually it'll structurally unsound too. And with all the other ones, 7-sided, 8-sided, like you can't take stop signs and just put a bunch of stop signs together and tessellate. That's just the way it is because of the way the interior angles come together. They have to be able to come together and make 360 degrees around. And your equilateral triangle, your square, and your regular hexagon are the only ones that can do that. Now don't despair. These are not the only kinds of tilings. I was just saying those are the only kinds that you can do with regular polygons. If you want to take the single regular polygon and tessellate it. But we have other options. In fact, we have something called semi-regular tilings. There's 8 of these possible. In fact, one of my textbooks has a really nice image that shows all 8, but for copyright issues, I'm not going to put the image on here. But if you do a Google search for semi-regular tilings, you should come up with pretty quickly with a page that'll show you all 8 and what they look like. These do use regular polygons. But more than one type or size. So this expands your options. You know, I mentioned earlier that you can't just tessellate a stop sign, because if you try to do that, you're going to have gaps. But if you consider those gaps when you try to tessellate your stop sign, and you think about those gaps and what kind of shapes they are, you can then use that shape and do a semi-regular tiling. Start drawing this, you might start kind of recognizing those shapes. Again, my drawings are bad, so if you don't recognize it right away, that's my fault, I'm sure. But you can start tilings with squares and octagons. And that works. Actually, I've seen tile floors like that before. I want to say it was in a restaurant or something, or maybe in a bathroom somewhere, but I've seen the octagons and squares together like that. And usually it's like white octagons and black squares. It's usually the color scheme, or like although the white usually is more of a gray and dirty, but whatever. So, so this is a possibility. This one you're using an octagon and a square. And that's a regular octagon. Some of the other possibilities, there's one that involves a hexagon and then smaller equilateral triangles. There's one that involves squares and equilateral triangles. There's, of course, this one. There's another one that involves squares and equilateral triangles, but it's a different pattern. One of them looks kind of like a stained glass window. The other, they're kind of lined up in rows more. There's one with a hexagon, a square, and an equilateral triangle. That one's really cool looking. It looks kind of like a kaleidoscope to me. There's one with hexagons and triangles. There's one with, how many sides is that? I think it's a decagon. No, 12 sides, a dodecagon with squares and hexagons. So that one's pretty cool. And then there's another one, I think it's 12 sides also. Yeah, so another dodecagon but with equilateral triangles. That one looks kind of like something you see under a microscope. It looks kind of like little bubbles and stuff, like when bubbles are touching but not quite together yet. But there's only 8 of those possible made with the regular polygons. And the thing about the ones with the regular polygons is that they have something called vertex figures that helps you to see that these truly are semi-regular tilings. If you can draw vertex figures all over it and you can get the same vertex figure shape over and over again, then you know you have a semi-regular tiling. If your vertex figure shapes change, then it's just some other miscellaneous tiling. So like, what is a vertex figure? Well, when you go look at a vertex, a point where vertices meet here on these polygons. And if you take the midpoints of the sides that make up that vertex there, and then you draw segments to draw a polygon, you can do this anywhere on your shape. If it's a semi-regular tiling, you can do this anywhere on your tiling, and you will always get the same shapes for your vertex figures. So you can pick anywhere and do that, and it works out. So just take the midpoints of those edges that come together there, that vertex, and when you connect those with little segments, you can make polygons that all are the same shape. Forgive me, my drawing, it's hard to see that they're the same shape, but they are. If you used a ruler and measured this out and made it nice and straight, it would work better for you. Now, like I said though, you can have tilings where the vertex figures are not the same. You don't have to just have regular or semi-regular tilings. You can have other miscellaneous tilings too. There's nothing wrong with that. Like I demonstrated earlier that a regular pentagon can't tessellate by itself, but if we took a pentagon that's not regular, for example, those of you who play baseball or softball, if you took one that looks like home plate, or it might look like a house to some of you, if you draw like I do, that's how you might draw a house, you can tessellate those. So it's starting to look like row houses like in England, or maybe like the Painted Ladies in San Francisco. So you can tessellate those. Like up here, you can turn them upside down. It reminds me when I was a kid, I used to watch a show called Picture Pages, and I remember like seeing pencils all lined up on the intro. Kind of reminds me of that. But anywho, so you can tessellate the pentagons that aren't regular. And that's fine, that works. I've seen tessellations like that before too. And if you start to investigate your vertex figures, you're going to find that they are not the same all the way throughout your tessellation. Some of them are. So like right here, a little vertex, we'll connect our midpoints of our edges that make that come together at that vertex. We have this nice little triangle. But if we expanded our drawing, and let's say we do this. In our tessellation. This vertex here, vertex figure is not a triangle. So you might have some vertex figures that are the same triangle. You might have some vertex figures that are the same quadrilateral. But the fact that you have one that's a triangle and one that's a quadrilateral means they're not all the same. It's not the same throughout your tiling. So that tells you that it's not regular or semi-regular. All right, so you know who was a genius at working with these? Mentioned him earlier, Mr. Escher, M.C. Escher, Moritz Cornelius Escher, famous for his art involving tessellations and also physical impossibilities. And some of his art too is just more of a self-portrait nature, but he was brilliant with those as well. Was not formally trained in mathematics, but his art was often very mathematical. And then he ended up developing a branch of mathematics called crystallography that helps to categorize crystals. Very useful in geology. On one of his works, Circle Limit 3, actually in more recent times, I know 1995 is not that recent anymore, but within my lifetime, it was proven to be consistent with mathematical theory. So mathematicians actually were able to sit there and analyze his art and see that it was indeed, like, were able to prove that it is mathematical. If you want to check out some Escher resources, I mean, normally in class I would show you my giant book of Escher art. I love that book, but I can't show you that on here. But you can go to mcescher.com and see some examples of his art, or you can just do a search for MC Escher art. Find all kinds of stuff about it. Or if you're more of a Lego aficionado, like my boys here are, you can check out this website that I have listed, where they took select MC Escher works of art and recreated them in Lego. It's pretty cool. Interesting how they did some of the tricks they used to make the Legos try to look like some of the physical impossibilities in some of the artwork. Because he does a lot of optical illusion type stuff in some of his art. So it's interesting to see how they created that in Lego. All right, and in your projects, you're going to create a tessellation. I mentioned that earlier, but I'm going to emphasize it again. You have a nice project where you're going to pick one of 3 types of Escher-like tessellations, and you're going to follow the directions to make one. You're going to end up making this little cutout template thing, and then when you follow the directions for tracing it, once you fill up your whole paper with tracing this, it'll make a nice tessellation. If you do it properly, you will not have any gaps or any overlaps in your figure. You'll have the same image repeatedly used over and over on your paper. Some of you, it'll fit together as you just go across the page, and then you'll reflect it and go across the page again, like flip it, go across the page again. Others of you will have to rotate. It just depends on which one you picked. But you're going to do that, make it colorful, fill up a whole paper, make it colorful, and then you're going to post it and then share your artwork with your classmates. And then you guys can take a look at other classmates, and if somebody's struggling, you can try to help them out. Or if you just think their artwork is awesome, you can comment on it and, tell them that, hey, that looked really awesome, or talk about maybe what they analyze and decide, if somebody else's artwork is better, maybe you can analyze why, and then talk about that. All right, so when you go to do your tessellations, there's a couple of terms I should probably lay out here for you to be familiar with. The process you're going to be using as you make your tessellation, once you make your little template, you're going to use rigid motion to get that template all over the paper and to have these images. And when you're done, it's going to be kind of like your figure moved across the paper. If you have an imagination, or if you're into animating things, you could picture your template dancing across the page and stamping the paper. But a rigid motion is where you it's like you move a geometric figure from a start position to a finished position without altering the figure's shape or size. So your little template, you're not going to alter its shape or size once you have it made. You're going to start out, you're going to trace it on your paper somewhere. And if yours involves sliding it across the paper, making sure it matches up front to back, if the back end has to match up with the front end, then you're going to trace it again. And when you're done tracing, marching across the paper and tracing, it looks like the image moved across the paper. If yours is rotational, then you're going to rotate it and get that same effect. Okay, so a couple more terms that you're going to need to be familiar with as you pick out which one you're going to do when you're going to do it. One is reflection. For some of the projects, you might have to do some reflecting. Let's say your image, this is not going to be one of your images, but let me just draw a parallel or a trapezoid here. In a reflection, you have a line of reflection. think about that as a mirror. So your same exact image gets flipped over and is equal space from your mirror or your line of reflection. It might involve a translation or glide. So that's where your shape's sitting in one position, and you might have to slide it over into another position. Yours might involve a rotation if you pick that one. So you might have your image. You might have a particular point of rotation. So imagine you're sticking like a pen inside of that dot there, and then you're able to spin your paper around that dot and then draw your image again. So you might end up with your image over here. That's a rotation. Or you might have a situation involving like a glide reflection, a combination of the glide and the reflection from earlier, where maybe across the page, you start out with this image, you might glide it over and trace it again, glide it over and trace it again, glide it over and trace it again. But then to get the next row, you reflect it and trace it again. But then you're gliding it and tracing that reflection across the page. So there are some of the projects that look like that. So that's some of the terminology that you'll see when you're reading through your projects. All right, and as you're working, if you want to check out some more cool Escher resources, there's this first website. It's pretty cool. It's like if you ever play with an Etch-a-Sketch, it's kind of like that, where you can draw an image and then it automatically reproduces that image in such a way that it tessellates or tiles your whole screen. And then for those of you who like shows like Warehouse 13, kind of a pop culture sci-fi type show, if you're into that kind of thing, if you've never seen this, find Warehouse 13 and watch it. It's an awesome show. But in one of the episodes, they have an Escher vault place. They have something locked away, but it's the vault, the staircases and everything move around, but when you look around, it's basically an Escher artwork put into motion, 3D and in motion. So that's pretty cool. Or if you don't want to watch the whole series or show or whatever, I'm sure you can do a Google search and find, or maybe on YouTube find Warehouse 13 Escher Vault. So that's pretty neat too. I had to include that. Yesterday when I first tried to do this video, I was wearing my Warehouse 13 t-shirt. It's like, okay, definitely have to include that example. All right, well, I think that's it for this lesson. Thank you for joining me. When we do the next lesson, pretty soon we're going to be approaching fractals, which is like my favorite thing. So we still have a little bit more to go in this geometry unit. But have fun with your tessellations and see you again soon.